Hello students. Today we will start a new chapter. This chapter is being called as equilibrium. This is the lecture number 1 presented by me, Pranit Ghatak, your chemistry teacher. So, let's begin. Here in this class we're going to deal with what is equilibrium, the types of equilibrium and how any reaction can attain this equilibrium and what is equilibrium constant. Okay. So we will deal with all of these factors and parameters. Before we start, what is equilibrium? We need to know there are two types of reaction. One is reversible and other is irreversible. Reversible reaction means when a reaction goes only forward way, that is from A to B, and the sign is unidirectional. Sorry, the sign is only one directional or unidirectional. Okay, but this is being called as irreversible reaction. Irreversible reaction. Okay, but on the other hand, if the reaction goes like this way, it can go on the both of the side, that is from forward way and backward. Then the sign will be like that only. Okay, so just give me another color. Okay, so if we take a reaction like that, A is being converting to B and B is also converting to A. So from A to B and B to A, both the sides are being open. So this reaction goes on forward as well as backward. This reaction is being called as reversible reaction. Reversible reaction. Okay. Here look at the signs of reversible and irreversible. For reversible the signs are like this, both forward and backward. This is being called as reversible sign. Okay, and in the case of irreversible, this is only unidirectional sign. Okay, only one directional sign. Okay, so this is being the concept behind the reversible and irreversible process and reversible and irreversible reactions. In the case of equilibrium is basically the chemical equilibrium is being a dynamic condition in which concentrations do not change and the rates of forward and the reverse reactions are equal. Okay, so what is a chemical equilibrium? Chemical equilibrium is basically a condition where the rate of forward reaction, that is from A to B, this is being called a forward reaction, and from B to A, this is being called a backward reaction. So the rate of forward reaction and rate of backward reactions being the same. As the rate of forward reaction and the backward reaction is same at that condition, so that is why the concentration of reactants and product do not change. So basically in chemical equilibrium, what happens, the forward and backward reactions are at the same speed. Because of their same speed, that is why the reactants and products concentration doesn't change. So this is being called as the chemical equilibrium. Okay, so this is a dynamic condition, and so reactants are making product at the same time the products are making reactants at that point of time, that is being called as equilibrium. Okay, and equilibrium are of two types, mainly static and dynamic. As I already discussed about the sign, that is the reversible sign, this is being also called the equilibrium sign as well. Okay, so the equilibrium sign is used to show both the sides of equation are present. Okay, so what is static equilibrium? When all the reactants particles remain as the reactants, they do not convert it to product. Okay, and all the products remain as product, they do not convert it to the reactants, then this equilibrium is being called as static equilibrium. So if there is no conversion of product from to reactant and reactant to product, is being called as the static equilibrium. So they are remaining still. Okay, so A doesn't convert to B and B doesn't convert to A. In this condition, then it is being called as the static equilibrium. Or A remain as A and their concentration still become the same, whereas B still become B. They cannot convert it to A, and as it is not converted to A, the concentration of B remains same, exactly same, and this condition is being called as static equilibrium, where the reactant only stays as a reactant, it cannot convert it to the product, and the product stays as the product, it cannot convert it to the reactant. So if in this condition the interconversion of reactant and product is prohibited, this is being called as static equilibrium. And what is the dynamic equilibrium? When there is a constant exchange, there is interconversion of reactants and products constantly, is being called as dynamic equilibrium. So when from A to B and B to A is being constantly happening, and as it is constantly happening, so and the rate of change of A to B and B to A is same, that is why the concentration of A and B remains constant. So that is why it is being called as the dynamic equilibrium. Remember, in the case of dynamic equilibrium, the interconversion of product and reactant is occurring, but here in the case of static equilibrium, the interconversion of reactants to product is being prohibited. Okay, so this is the basic difference between the static and dynamic equilibrium. Okay, look, so what is equilibrium? Basically, we know that this is, suppose this is reactant, this is the graph of reactant, and this is the graph of product. Okay, so reactant, when we start the reaction, reactants will decrease. At some point of time it will become still. Similarly, when in the case of product, as product is being forming, so it will be, the concentration of product will increasing step by step, but after some point of time it will not increase, it will be constant. Like the decrease in concentration of reactants is equal to the increase in concentration of product. So all of this become same, this becomes almost same, this graph becomes almost same, and the slope of the reactants and products is getting almost same. So that is the point where it is being called as the reaction is in equilibrium. Here you can see in that position the change of reactants and products is minimum, so that is being called as the equilibrium position. Okay, so let's see an example where you can see that this is a reaction of Haber process, that 3H2 plus N2 that gives us 2NH3 plus heat. Here you can see these are the being reactants, and this is converted to product. This is the NH3 is being product. So here this is sign is being equilibrium sign. So that means the reactants, that H2 and N2, they react with each other and it will form NH3. Similarly, this is the forward reaction. So from reactant to product, this is the forward reaction, and from product to reactant, that is from NH3 to the decomposition of NH3. That means the NH3 will decompose and it will form N2 and H2, and this reaction will be called as the backward reaction. Okay, the forward reaction, the rate of forward reaction and the rate of backward reaction will be same. So that is being why it is being called as dynamic equilibrium. Okay, or this is being called as the chemical equilibrium. Okay, so this reaction holds good for chemical equilibrium, that is denoted by the equilibrium sign as well. Okay, so let's proceed to the next point actually. So thus all the reaction can attain equilibrium or not. To attain the equilibrium, all the reactions should obey three requirements. The requirements are basically, these three requirements are basically, the reaction must contain or must occur in a closed container, number one. Number two, the reaction must be a reversible reaction, as I have earlier told you that in the case of reactions there are two types of reactions, reversible and irreversible. To be equilibrium, or to be attaining equilibrium for a reaction, it is mandatory for any reaction to be a reversible reaction. Other than a reversible reaction, this sign couldn't be achieved. Okay, and the third parameter is, or third condition is, the reaction must have plenty of chemicals to begin with. Okay, because to start with we need a huge amount of chemicals or reactants. If the reactants amount is less, then it cannot be proceed further. Okay, so to attain equilibrium for any reaction, there are three conditions. That is, number one, the reaction must occur in a closed container, then number 2, the reaction must be a reversible reaction, and number 3, the reaction must possess huge or plenty of reactants materials. Okay, so these are the 3 conditions. If any reaction have these 3 conditions, there is a chance for that reaction to achieve equilibrium. Okay, so let's move to the next point, that is the equilibrium constant. To the equation to calculate the equilibrium, or the equation to calculate the relationship, is being called as equilibrium expression, and in the case of equilibrium expression we have equilibrium constant. Okay, so equilibrium constant is basically what? Is basically the ratio of products to the power coefficient, stoichiometric coefficient, by and the reactants to the power stoichiometric coefficient. Suppose in the case of A, suppose 2A plus 3B, that makes 4C. Okay, the color is not such 4C. So what will be the equilibrium constant? The KEQ or equilibrium constant will be product to the power its stoichiometry. Here the product is C, the concentration of product, that is C, to the power is stoichiometry. Stoichiometry is 4, so to the power 4. Here in the case of reactants, A, concentration of A to the power 2 into concentration of B to the power, the stoichiometry, here the stoichiometry is 3, so here it will be 3. So in this way we will get the equilibrium constant. So equilibrium constant is nothing but a constant, that is the ratio of product to the power stoichiometric coefficient and the reactants to the power concentration of reactants to the power stoichiometric coefficient. Okay, and to evaluate the equilibrium constant, we need to know that we only use the gases and the aqueous solutions to evaluate the value of KEQ or equilibrium constant. We doesn't carry solids and liquids, as they do not have any concentration, so we do not include the solids and pure liquids. Okay, remember, in that case, to evaluate the equilibrium constant, we only use gases and aqueous solutions, not pure liquid and the solids, because the pure liquid and solid doesn't have any concentration term, as there doesn't have any concentration term or doesn't have any proper concentrations. So that is why we exclude the solids and pure liquids. We only take gases and aqueous solutions. Okay, let's take an example of that. Suppose this is a reaction. This is propane C3H8 is being catalytically oxidation is being occurring here. There is 5O2 and it makes 3 CO2 and 4 H2. Here you can see that this all the compounds are mainly gases. There is propane is gas, oxygen is also gas, carbon dioxide is also gas. But here this 4H2 is in liquid, so we will not take this into the calculation of KEQ. So KEQ will be product to the power the stoichiometric product is CO2, concentration of CO2 to the power this 3, because 3 is the stoichiometric coefficient, and here by the reactant concentration is C3H8. There is no stoichiometric coefficient, so it will be only 1, and there is another reactant, that is oxygen, concentration of oxygen to the power 5, because 5 is the stoichiometric coefficient here as well. So this will be the equilibrium constant of this reaction, and here this will mention that H2 is not used because it is a liquid, it is a pure liquid. As it is a pure liquid, it is not an aqueous solution, so it doesn't have any concentration term with it. Okay, so we have to exclude that as well. So this is the topic of the day. Okay, in this is the lecture number 1, and this is the mainly introductory class or basic class of equilibrium. In the next day we will continue this chapter as well. Okay, so if you have any doubt regarding to this topic, please ask me in the comment section below. So thank you very much. Bye.